ZK-TLV Meetup for organizing this and talking. And it's nice to be here. Thank you all, guys. I think this is the second talk in a couple of weeks. It's nice. So as you see here, this is a zero knowledge meetup, and it says SNARKs in there, but thankfully, or maybe not thankfully for some that you expected, there's not going to be that much about SNARKs. It's going to be a lot about this thing that we call universal circuits, and I'm going to get into it in a second. This is work by Abel Adari, myself, Kobe, and Aviv, who are both here. So if you have any questions, you can also get to them. And great, so let's jump into it. I guess many of you are already familiar with zero knowledge. Some of you are experts in zero knowledge, but just so everybody's a bit in the same level for the talk, I'm going to kind of introduce quickly what zero knowledge proofs are. So essentially, zero knowledge proofs allow you to prove some computation on private data, right? Especially integrity of computation or correctness of computation. So if Alice wants to prove that she knows some value x, right, some secret value x, such that some function f of x is y, Bob needs some proof, right? He doesn't believe her. So there is a setup for some schemes. There is some kind of pre-process that are based on pre-processing of zero knowledge. There is a setup that is done through a trusted computation or ceremony to generate the proving key and the verification key. Then there is Alice, the prover, who generates a proof based on the proving key, some secret data, and some public data, which is kind of the query, right? The actual statement. And she sends the query and the proof to Bob, actually convincing him if the secret data that she has is or satisfies the function and the query, then the verification process is going to say yes, right? That's essentially zero knowledge proof in a nutshell. The main security assumptions or definitions kind of around zero knowledge proofs, these are the most well-known ones, is completeness, which kind of says it's correctness, right? It's if Alice, or in this case, Peter was my prover, but just forget about it for a second. If Alice, the prover, actually knows the solution, she will always be able to convince the verifier, right? This is correctness. There is soundness, which basically is about a cheating prover. So what soundness says is that a cheating prover will not be able to verify, to convince a verifier of a true statement if she doesn't have, right, the private data, and will be caught with some probability, right? Negligible, high probability. So he will be able to cheat, or she will be able to cheat with negligible probability. And zero knowledge is exactly what we want for in terms of privacy, which says that the verifier won't learn anything about the data except the query itself, except the fact of the proof, right? So in some sense, it's literally one bit that the verifier learns extra, right? The yes or no. So just a quick overview, I guess, of the main schemes that are out there today, like close to production or in production. There is SNARKs, which is succinct, non-interactive arguments of knowledge. There are STARKs, which are scalable, transparent arguments of knowledge, and bulletproofs. So each one of these have kind of their good side, their bad side, as you can see here. So for SNARKs, the proof side is basically constant. So it's no matter the size of the computation, the size of the proof is always the same. The prover time is linear in the computation size. So it's not exactly super efficient, but it's quite efficient for current applications and use cases, and the verification time is completely it's optimal, right? It's constant as well. The STARKs, so SNARKs actually, this is one of the reasons why we like SNARKs a lot, because it's kind of green and yellow and not red, except that it has this pre-processing phase, or some of the schemes have pre-processing phase, and it's a trusted setup. Now, STARKs, as you can see, have a higher or larger proof size. Prover time is pretty fast, specific for a specific kind of constraint systems, I would say, or problem statements. And the verification time is also pretty good. And bulletproofs are these schemes that are being now used in Monero that are kind of good for very small computations, right? So range proofs, for example, in cryptocurrencies are being now implemented with bulletproofs, right? But for larger circuits or larger computations, you probably don't want to use bulletproofs. So just to kind of close the introduction, I want to talk a bit, just 2 seconds, about this ZK-Proof effort, which is a standardization effort around zero-knowledge proofs, right? So there is a lot of implementations and a lot of constructions that are coming out even weekly in the space. And we gathered in May this elite group of researchers and industry participants that kind of sat together to create a common framework of how to talk about zero-knowledge proofs, what to create in terms of interoperability. And the second workshop is being planned for April. We encourage you guys to send us a request for invite, get in touch with us. You can collaborate. There is actually open source projects going on right now, both in terms of actual projects and like work for standardizing specific topics, right? And you can join all of these. So please definitely get in touch, zkproof.org. Okay, so let's now jump straight into what we want to talk about, universal circuits, right? So what's the motivation? As I was saying before, some SNARK constructions have this trusted setup. And the trusted setup essentially is needed because when you generate this proving key and verification key, there is an issue that there is some randomness that needs to be added into this trusted setup. And this can be actually is what we call toxic waste, right? This toxic waste means that if someone gets their hands on this randomness, then they can generate fake proofs, meaning that they can generate proofs that verify, but without having the actual private data that satisfies the constraints, right, the problem. So the way that this is solved is by using this MPC ceremony. I don't know if you've heard of Zcash, for example, that has already had 2 of these, one for each one of the versions of Zcash for Sprout and Sapling. And essentially, as Carsten said very well, like an MPC just generates a result on some computation with individual inputs, right, into the computation. So now each one of these parties will know what their own randomness is, but in order to reconstruct the whole thing, they need to kind of get it from everybody else, right? So as long as one, this is, again, there is toxic waste issues, but this has, this kind of computation has a very high cryptographic assurance, right, for honesty, because as long as one party is honest, out of the hundreds that there can be, then you ensure that the toxic waste cannot be recovered, right? And then the system is sound. So another setback of trusted setups is kind of that it's very expensive and takes a long time, right? I mean, Zcash, for example, went through, the second one actually involved something like 100 and something participants, 150 participants maybe, and it took a lot of time, like 3, 4, or 5 months to compute. Of course, it can be in less, but essentially it takes a long time. And another issue is that as soon as this function f, right, that we want Alice to prove on, is the same, then you can use the same keys. But if the function or this constraint system change a little bit, the whole ceremony needs to be recomputed, right? So this is very expensive for recomputation. And if you have, let's say, for example, in enterprise systems, many circuits or many kind of constraints that you want to prove for different parties, this means that, let's say, the bank or the insurance company needs to hold a lot of key pairs, right? This is usually also heavy. It can be up to gigabytes sometimes. Okay, so we've kind of outlined these negative aspects. So let's get a bit more specific. SNARKs, the SNARKs that have usually this trusted setup are based on arithmetic circuits. And the most common ones, and for the sake of simplicity of the talk, let's focus on arithmetic circuits and the instantiation or the representation of arithmetic circuits that is rank 1 constraint systems, or R1CS. So what are circuits? Circuits are basically directed acyclic graphs. They're DAGs. In this case, it's going to be fan-in, fan-out 2. As you see, there is several nodes and edges, right, like a graph. And essentially, there is a direction of input and output, right, where the directed part of the graph comes from. So an arithmetic circuit specifically is defined by computational gates that are additive and multiplicative. As in comparison to what we saw in the previous talk, that was a Boolean circuit because we saw ANDs and NANDs and XORs, gates, and so on. This is arithmetic, right? So it's kind of a bit more readable to the eye. And as I said, we use R1CS. Now, the interesting part of this is that it's very convenient to arithmetize, actually. So we can generate polynomials that represent this circuit and the constraint system, and essentially the verifier kind of does the prover does some magic, and the verifier verifies this relation between the polynomials. I don't want to get much into it because it's also not explicitly relevant to the talk, but it's worth knowing. Okay. So essentially, a statement, right, a constraint system would look something in the following sort. This is kind of a very simplistic circuit with a lot of multiplicative gates. In red, you see the private inputs. In blue, you see the public inputs. One interesting thing about arithmetic circuits or the use of R1CS is that, for example, we have addition for free, right? So this constraint says that you add x5 and x6 and then multiply by this constant times x7, right? So this is a very important feature that is used widely in implementations of circuits today. Essentially, when you want to change this function, right? So we have an instance for a function f and value y. This is known to everybody. The prover says, I know a witness x, and such that there is a relation of f of x equals y. This is kind of where we started. And this f can be translated into a circuit, right? So a multi-variable circuit, let's say. But again, I go back to saying that this is a not very flexible construction in some sense, because if we change f a little bit, we need to change and recompute the whole trusted setup again, right? If we change x or y, we don't, because that's what the function of the variables actually does. So how can we solve this issue of the trusted setup, right? There's some interesting approaches to this. So one that was originally in a paper by Ben Sasson, Chiesa, Tromer, and Virza. It's called TinyRAM. And TinyRAM is essentially this generic computation with an assembly language. So it's kind of with opcodes and is general purpose in the way of a random access machine. But has huge cost in computation. Every step of a computation requires even seconds to compute. That's some of the benchmarks that exist today. Essentially, you do also need to have this kind of recursive proof composition, because every step is proved and then in a general way, and then you need to put all of these proofs together in a recursive composition, which is not today is not exactly practical either. There is the powers of tau ceremony, which essentially says that if there is a set of random elements that need to be produced for the trusted setup, then we're actually going to generate most of those random elements and reuse them every time we're going to have to update the circuit. But there is this kind of last element that we need to compute when we fix the circuit in some sense. So this is what Zcash did for their last update of Sapling. So it's very nice because you can reuse a lot of these randomness, but it takes still a long time to compute. And essentially, we have the same kind of security assurance where if someone breaks the second ceremony or figures out the toxic waste of the second part, then they can still kind of break the soundness of the scheme. There's another work by Groth et al. That basically talks about this updatable CRS model that essentially says, we have a pre-processing SNARK, but we can now generate a set of keys, two proving key and verification key, that is general in a way that we can just update the keys without having to compute the actual trusted setup for every new circuit, right? So this is great because it's a one-time trusted setup. You have updatability of the keys, and you don't need to deal with the trusted setup every time. But this specific construction has an n squared overhead on the key size, n being the number of constraints, right? So this is really, really big. Today we're going to talk a bit more about universal circuits, right? So we've kind of studied a bit more in depth this solution because it's very interesting. It lies a bit. It takes a bit good trade-offs from all these solutions with some negative aspects that we'll also discuss. And the main good thing is that we have the ability to compute keys. To reuse the keys that we generated with this universal circuit for many different circuits up to a fixed size of, like, let's say n gates, right? So any circuit that you have that is of size n gates, we can just use the same pair of keys, right? And just reuse them without generating the new trusted setup. This allows in some sense for key batching. Again, if an enterprise setting, you have many circuits, you can use the same pair of keys, right? You don't need to keep recomputing or updating keys. This, though, gives you an overhead of more than n log n, but around n log n in asymptotics in the circuit size, which is also a lot, but in some cases it may be worth exploring or using. So the overhead in powers of tau is there is no real overhead in the actual key size or circuit size. It's the same as before. It just takes a long time and it's divided into 2 ceremonies and so on. But it's not. You still need to do a trusted setup for every circuit in powers of tau, right? Because you have that second ceremony that always needs to be used when you want a new circuit. Yeah. Yes, correct. It's linear in the number of constraints. Okay. But that's like the usual construction of SNARKs, for example. Okay. Good. So let's dive a bit deeper. Do you have any questions up to now before I continue? Okay. So the first instance of universal circuits was published by Valiant in '76. It's a very interesting construction and kind of computer science primitive in some sense. And there is follow-up works that when I share the slides, these are all linkable, so you'll probably have access to the papers. And in one sentence, so universal circuits are essentially programmable circuits, or in this case, arithmetic circuits, with some kind of a flexibility similar to FPGAs, right? So if we were talking before about TinyRAM being similar to like a processor or random access machine, FPGA is like universal circuits, and then you have like ASICs, which is like complete opposite of complete specification of the circuit, right? So what do we mean by programmable? In a graph or in a circuit, we said we have gates or nodes and edges which define the direction of the inputs, right? So we can program the gates to be maybe more than one operation, and we can program the path to route the different input nodes into the gates, right? So what do we mean by programmable gates, right? Let's say we have 2 different gates, an addition gate and a multiplication gate, right? Where x plus y equals z or x times y equals z. So now we can actually combine them and create what we call a universal gate. And the only thing that changes in some sense is this extra bit that is a programmable bit that essentially will tell the universal gate, hey, I want to compute an addition or I want to compute a multiplication, right? So as we said, this universal gate computes one or the other. And let's see exactly how we can actually do it. So this is an example of how we would actually build it in terms of constraints. So this sub-graph or sub-circuit, let's say, it represents a universal gate, right, in the 3 gates there, which basically says, if C is 1, then I'm computing Z1 plus Z2, right? If C is 0, then I'm computing the multiplication. And I'm not going to go specifically over this, but you can see that, here if C is 0, then all of this goes away, and then this stays, right? So it's kind of, it's not so difficult to see. And this would be a universal gate for addition and multiplication. we can take several of these and put them together to kind of create a universal circuit, right? This is kind of the first intuitive step that you can take to construct a universal circuit. So you have several inputs, and you have several programming bits for, let's say, each of the universal gates, and you have some outputs, right? And all in all, if your original circuit was of size n, this new universal circuit could have potentially an increase of a factor of 3.5 larger number of gates, right? This is only due to the gate universality, right? I will get into the routing part now, because essentially now you have a lot of gates, you have a lot of inputs, but you need to route the inputs into the gates, right? This is also part of the essence of universal circuits. It's great. So when we say programmable paths, we mean exactly that, right? If we have a couple of or 3 gates, now we're computing these gates in different ways. Here I'm missing the programming bits, but essentially the programming bits can now also decide which input is going to be, let's say, in the right side, right? We said it's fan-in 2 gates, so in the right side or in the left side. As you can see, it's either X3 or that gate, or X2 and this gate. So again, this is something that happens in the universal circuit. And the cost of routing is actually larger, and this is where the main cost comes from. It's n log n, right? Which is not trivial overhead. Great. So in general, how does the procedure to actually create a universal circuit that can be used, how does the procedure go, right? So we first need to define the computation, meaning that we have our circuit. We get our original circuit. Let's say it's this very simple node structure that represents f, right? That we want to compute f of x on. And in here we say that it has 4 nodes specifically. And now we want to actually embed it. Let's for a second assume that this is our universal circuit, and we want to embed the circuit C in this. So we take an algorithm A that is kind of what Valiant and these other constructions discuss more in depth, and which takes in this circuit C and outputs these programming bits to define how to essentially embed the original circuit in the universal circuit, right? Very important is that if the universal circuit has n gates, then at most n gates, then the circuit that you embed cannot have more than n gates, right? So here you can see, for example, that this would be a way to embed it. And the algorithm would generate the bits, the programming bits, both for the routing. So it would take C, A, D, and B to the right positions and compute the right functions at each of the gates. So the main difficulties with universal circuits when applied to SNARKs essentially are that, one, we now actually don't have addition gates for free, right? So before we saw that we use this bilinear constraint system, whatever that means, that allows us to use linear combination as inputs of data, right? And not only actual elements of groups and things like this, but actual linear combinations. And this means that the addition is free. But now we do not have that, because we need to specify what is the computation or the actual function inside of the universal gate. And in some of the use cases that we've implemented, we have actually about 1/3 of the total gates that are addition gates. Next, we have that there is a large overhead, as we saw, of about n log n with some constant in the number of variables and in the number of constraints by the programming bits. Because routing is not only about inputting programming bits, but there is also specific gates that are called routing gates, right? We'll see an example of them in a bit. And essentially, 1/3 negative aspect is that sometimes you actually may not really need n gates, right? Maybe your circuit has, square root of n, who knows, like log n gates, right? It's a really small circuit, and then you actually end up using an embedding or a universal circuit that has much larger gates, and your overhead is extra, or you have an extra cost basically for nothing, right? You're not using up the potential in some sense. So this can also be an issue. So let's just quickly go through this kind of construction of Valiant. Essentially, Valiant says, start by defining a universal gate that kind of encompasses the computations that you require in your function f. essentially, if you're doing addition and multiplication, this is enough because usually, you can compute anything in MP from multiplication and additions. Then it says, okay, now we need to actually route the inputs through the gates, right? So we're going to do this embedding recursively. We're going to start with kind of the universal circuit, and we're going to look at each gate and separate from left and right inputs and outputs. And we're going to route the left on one hand, and we're going to route the right on the other hand. Now, what this allows is to kind of create this n/2 separation, right? In average, you're going to have n/2 gates on one hand, n/2 gates on the other hand. And what you do is essentially you do this decomposition recursively until you get to kind of one node that you can actually embed by hand even, right? This is a trivial action. And this is kind of a representation of what it would look like if you have this universal gate and left and right inputs and outputs. You can end up with something that looks like this, right? In essence, this left output comes to this routing gate and says, the routing gate tells the output to go to the next routing gate instead of going into the next universal gate, right? And this is kind of where the routing happens. But as you can see, we separate from the right-hand routing and the left-hand routing. And the construction is essentially kind of looking at this, right? This kind of recursive construction where if you look at the middle layer, this is the actual embedding circuit, like the original circuit that you want to embed, is represented by these n gates, and all the routing happens through these n/2 or n/4 or n/8, etc. decomposition of the routing, right, of the gates from the left and the right. Great. So one example of routing gates, right, is or two examples in this case, is these two gates. This is what also Valiant gives in the or one of the follow-up works in their construction. One is the Y gate that basically chooses one of the inputs and outputs it. Right, so in here, if C1 is 1, then we see that the output is actually Z1, and if it's 0, then it's Z2. And the other gate that we have is this switch gate, right, which basically switches these two inputs order, right? So this kind of, you can see in the graph that I showed before that whether it can go on one direction or another, right? So here, as you can see, the output can be either Z4, Z3, or Z3, Z4, right? Depending on whether C2 is 1 or 0. Good. So, okay. Just before I continue, any questions? Because I know this may have been a lot of technicality too. Okay, good. Well,
yeah,
sure.
So if I understand correctly, basically C1 and C2 are sort of int you give to when you compile your circuit, you have C1 and C2 where it's going to be like sort of int of what you kind of computation you want to do. How does it relate to existing kind of constraint system?
Yeah, so if I get your question right, essentially the C1, C2s, and so on are bits, right? There's ones or zeros, and they are used to do two things. One is define the actual computation that is happening at each gate. So it can be either an addition or a multiplication, for example, or it can be used to kind of tell the inputs to which of these gates to go, right? This is what I mean by routing. Was that your question? Maybe
no, I understand the routing part. I just mean that, so since these circuits are universal, let's say I want to do some computation for F1F, and then I want to do J. I want to provide an X that output to that Y for that J.
So you'll have different programming bits.
Yeah, we'll have different programming bits. So the programming bits would be sort of would be provided as sort of a share. Like when I want to generate a proof, I would have this pre-compute kind of bit available for me to check. Okay.
Right. So, okay, maybe I'll just get here. So we saw these universal circuits, and these essentially can be translated now to universal R1CS, right? And everything here is still, let's say, okay, except the embedding, the universal construction itself is actually separate or before the actual trusted setup, right? So we compute this universal circuit, then we translate into universal R1CS that we call, and then we generate the trusted setup and the keys for which every new circuit there is a very easy algorithm that will output the programming bits, right? For that specific circuit. And then the programming bits can use that as a public input or actually private, but we'll see that in a second, public input into the verification process, right? In some sense, it's known up beforehand. So just a quick review here of how we kind of translate this into R1CS. Oh, sorry.
Another question. You say you only use multiplication and addition. But you need to have negation also, to have like a fully
Sure. So what I didn't say before is that you can also kind of hard code constants, and then these constants you're gonna have a -1 constant, and then have a addition of that kind of thing and multiplication of that, right? This is a trick that is maybe I kind of assumed it.
So that doesn't have any other cost, any additional
just
cost?
addition cost.
Mm-hmm. Okay.
Yeah. Okay, so just, okay, no one else? Yeah, good. Okay. So going back to this, just quickly, essentially there is this added cost for R1CS, right? The programming bits become input bits, so this means that you increase now the size of the witness or of the query. The routing gates become constraints, usually several constraints, not just one, which means that it can be expensive if it's this is where the n log n part comes from, and the gates inside the universal gate now kind of are sub-circuits of your universal circuit, right? And or of universal R1CS, and generating a witness is now a bit more expensive, essentially, but not so much. Okay, so this is some concrete numbers that we have from a couple of implementations. As you can see, we have for original circuit with 10 multiplication gates, it gives you a number of 280 constraints in R1CS, right? All of these numbers are basically with essentially full universality. Okay, this is kind of the idea, where all the gates are universal and all the edges are routing edges, universal routing edges. In this case, the universal circuit could hold up to 40 nodes. And if we go all the way down, we see that for 10,000 constraints for a real circuit, you actually get almost 1 million constraints in the universal R1CS. This is a huge 100x increase, right? I mean, it's pretty big. And in general, it took kind of 27 seconds to generate these routing bits, right, for different circuits. So of course, this is not ideal. This was also highlighted in the previous works, not specifically around SNARKs, but in general, there is a known overhead. And graphs can get pretty big. I'll give credit to Abel because he actually got these graphs generated pretty nicely. And you can see here, for example, what we were saying before about these kind of routing decomposition methodology, because all these green edges in the middle represent the actual circuit, the original circuit. And in some sense, you can see that they lie in the middle, and all the gates outside, they're actually routing nodes. So in some sense, it's nice because the routing happens in the outside. And because these are DAGs, you could actually potentially linearize all of it and see exactly what are the gates that are being skipped by every single node, right? Every single input node. So it's very nice, but as you can see, there is a large overhead also from the green to the red and the black nodes. Good. So that's kind of universal circuits. Now, we realize that, of course, these specific constructions are not efficient. So we set out to kind of think of ways that we could improve this to actually be usable. And we came up with what we call hybrid circuits, right? It's kind of specifying a bit this universal feature. So what do we mean by that? in most of the use cases, we always have some subset of the constraints that we know that are fixed, right? If you want to compute SHA-256 function or some kind of commitment, or you want to compute or verify the path in a Merkle tree, right? These are things that are standard and that they're going to be fixed. Every time you want to compute this, you don't need to create a universal gate for every single gate you're computing inside, right? So for the case of the SHA-256, for example, this is about 30,000 gates that you don't have an overhead for. And if you look at the scheme below, the gate before, at the table before, sorry, for 10,000 constraints, you had almost 1 million gates of overhead. So this is a pretty good efficiency improvement. And in a similar way, not every path, not every input needs to be routed universally, because again, if you always know that your input x1, x2, and x3 are going to be hashed into one function, into one hash value, then you don't need to route them through every other gate, right? You know that this is fixed. So of course, this is not optimal for actually generating the circuit, but there is very interesting ways of doing it. And you gain a lot of efficiency from this. And an extra step could be taken in some sense if you now want to kind of go back to having a very specific structure in terms of the actual computations that happen in the circuit, right? You can keep universality of routing, but now you can actually completely get rid of the universal gates. If we have this kind of layering mechanism where essentially inputs come in and you first extract the variables and unpack them, then you compute kind of a scalar multiplication and add all these elements or terms that essentially gets you a linear combination that you want to use, such as in the first place with R1CS, right? And now you just kind of copy them around in the different gadgets that you have, right? Gadgets meaning like SHA or signature verification or so on. And again, this is not ideal, but it's much better than the actual universal circuit construction, and it gives you a lot of universality, right? In this case, you have a bit of a constraint that you need to say in advance how many variables. What's your maximum number of variables? What's your maximum number of scalar multiplications, and so on, right? So it's not ideal, but it's much better. So now let's see how we can actually use this, or what are the real applications of these, right? So we were saying earlier that we have this kind of one-time trusted setup, right? Because now you can actually generate once these proving key and verification key and reuse them for many circuits up to a specific size of n gates, right? We have the ability of updatability, right? But updatability not of the keys themselves, but of the actual network. Like when you're looking at enterprise systems or even like public systems, you need to, every time there is a change, you need to update the actual keys, you need to update the circuit, the whole system needs an update. If you look at Zcash, for example, what they did was they actually had to unshield every single transaction to then kind of unshield them, right? They have this mixing pool and mechanism that gave privacy assurance, but it wasn't, some people saw it as kind of a privacy issue. But in this scenario, you wouldn't need those kind of updates because the keys would be reusable, right? But you do have an overhead in the key size when you have one circuit. I'll put it in parentheses. And thirdly, we have key pair batching. So this I also mentioned in the beginning, where now if you have several circuits or several constraint systems that you want to prove on, you can use only one key instead of having hundreds of keys that you need to kind of choose from and hold in storage, right? And this really is a meaningful improvement for storage when you have a large number of circuits. And I think this may go back to the question that Louis asked before. You actually have this feature that comes with the universal circuits that is called circuit privacy, right? So now we were saying that when you generate a new circuit, when you want to embed a new circuit, you kind of generate these programming bits, right? And these programming bits, you can give it to the verifier for the verifier to actually compute the verification, right? Knowing what the computation was, because once he has the programming bits, he knows what the computation was. But on the other hand, the prover can now say, okay, actually I'm going to put the programming bits in the witness, meaning in the secret data, in the secret inputs, and I'm going to hash them and give the hash as a public input, right? In the circuit, then you can just verify the hash of the bits. And this essentially hides what is being proven, right? Like the computation itself, which can be very useful for some scenarios, which I'll say in a second. And it also allows for better communication complexity, because if you have hundreds of thousands of or even millions of programming bits, that is a toll that you pay in terms of the public input size, right? That needs to be sent to the verifier. So let's kind of recap a bit in terms of the different trade-offs and the different positive and negative aspects of using universal circuits. So we said if we have several different circuits, right, what would be the size of the keys, right, of all the set of keys that you're using? So for a regular setup, it will be huge, because if you have 100 circuits, you need 100 pair of keys. Each one can be up to like a gigabyte, let's say. This is bad. Universal circuits, well, it gets much better, but because of the overhead that is pretty large, then you actually have one key, but that is pretty big, right? It's not as big as 100 keys, but it's still big. And in quotations, it depends on the circuit itself. And in the hybrid situation, because we are removing a lot of the overhead, the keys size is much better, but you still have one pair of keys. Now, for circuit size and proving time, the regular setup is much, much better, right? No, there's no way of arguing with this. And that's why we kind of, if this is used, we would say to use it with small circuits. With universal circuits, the circuit size is the worst, and hybrid, as we saw, there is still an overhead, but not as big. Verification time, this is actually a property of, an inherent property of the SNARK, as we saw at the beginning. It's actually, in some sense, almost constant or sublinear in the circuit size, so it's very good for the three of them, because it doesn't matter what the circuit size is. And in terms of flexibility, in terms of reusability, updatability, and so on, well, we've seen that universal circuits has the best. Hybrid circuits, because you have some kind of constraints that you put to yourself, in sense of if you put a SHA, then that SHA is always going to be there, right? You cannot kind of change it to other things. And of course, regular setup is the worst, because you don't get any of these extra features. Great. So, as from a perspective, from the point of view of QED-it, that again we're targeting enterprise solutions, this comes in handy when we actually, for example, we have this methodology for circuit decomposition, where we can divide a big circuit into smaller circuits, and now we can actually compute. So some of these circuits can be don't need to be modified. And some of these circuits will be modified a lot, right? This is kind of the simplification that we make. And for these small circuits that can be modified, universal circuits can actually be great, because if they need to be modified often, maybe by a regulator, maybe by banks, maybe by insurance companies, health companies, etc., this is actually great, right? Because you don't need to have all the issues of deployment and updates and regeneration of a trusted setup and so on for small changes. And of course, more good things is, as I was saying, these function privacy use cases. For example, in the insurance risk computation, where the insurance company don't usually want you to know how they're computing the risk, right? But you still want to get kind of a proof that the risk was computed correctly. And other cases of proprietary software, right? I mean, this is kind of the main use cases. So, yep, and
what did you mean about
so proprietary software, meaning if someone needs to prove, so let's say I'm a company that owns some software, some actually computation that I don't want to disclose, then I can compute some data, I can compute the actual computation.
What do you mean the certificate?
Just
Indicated all the simple hash. I'll repeat my question. I didn't understand what is the benefit of using these techniques to prove a proprietary software is owned by some entity. That's what you mean?
No, that's not what I meant.
Ah, okay.
When I mean function privacy, I mean that, let's say there is some proprietary software. I, as a company, own some proprietary software, and I'm going to compute some data on this software. The result of this data, I'm sharing it with you. But if I compute a proof of correctness of computation with you, you're going to know what the actual computation was. So you can kind of reverse engineer the actual software from that. But now with this technique of hiding the programming bits, you can keep that private even into the verifier.
Thank you.
Thank you for the question. Yeah, so if you have any questions, thank you for listening. And we're hiring, guys, so please come to us. Yeah, please.
So say, for example, if I have a DLT infrastructure, whether it's blockchain, something like Ethereum, or non-blockchain like a DAG, like IOTA or whatever, how can I use a universal circuit? Where does it fit in?
So I guess there is several applications in general of universal circuits, but one is exactly what I just showed, like for SNARKs. So if you're going to prove some computation on a ledger, for example, then you want to be able to have kind of this flexibility, right, and get rid of this annoying trusted setup that exists.
Like what? Get rid of what?
The trusted setup, like essentially the key generation process.
Okay.
Right.
Okay. So you did speak about several use cases. Are any of them production ready or just pilots that are being tested on?
No, I'm out of my knowledge.
For universal circuits.
Yeah, from my knowledge, there is nothing using universal circuits, at least not for SNARKs today. Yeah.
In the other fields, there's nothing that's still being used or deployed at the present, right? Is that what you're saying?
Yeah, not that I know of.
Thank you.
Yeah. Sure. So I guess FPGAs is the one similar application of universal circuits. Any more questions? 1 second. Yeah.
1 second. Can you repeat?
What is the difference between the FPGA and the ASIC that you mentioned in the...
And the ASIC?
Yes, you mentioned it in the
So
start.
essentially, FPGAs allow you to kind of change the computation that is underlying in the hardware, right? Both FPGAs and ASICs are hardware chips or hardware circuits, but FPGAs allow you to change a bit the actual computation, whereas ASICs are completely
So you can
fixed.
program it?
Yeah.
Okay.
To a certain degree.
Any more questions?